starting from the observations. What observations is quantum mechanics? What observations, scientific observations, is the theory of quantum mechanics?
Movement of atoms.
I'm sorry?
The movement of atoms.
No. Not the movement of atoms. Something else. Yeah, one of the things I'm going to start doing is, because one of the things that you probably should do is try to summarize things in your own words, after we talk about them in class. But I'm going to summarize them for you in my words, basically, now. So what we're going to do is we're going to stop, and then we're going to go back and look and see, what we covered, and try to come up with a picture of what we covered, mental picture of what we covered. And I'll use my words, but you can change them around into your words and make it more memorable that way. And so what we're talking about the development of quantum mechanics, the theory of underlying chemistry. And so to just talk about the story is, we want to understand the periodic table up there. We want to understand the charts, like the oxidation reduction chart up there, the acid-base chart up there. We want to understand these charts. These charts are based on experimental observations. So when you look at those charts, what kind of hypothesis can you come up with? What kind of, we definitely see the patterns there. And so we got to hypothesize some kind of fundamental explanation. And so at the beginning, I said that, people tried to come up with a hypothesis. What are you going to come up with? You go from hydrogen to helium to lithium, the properties are so different. Can you come up with a hypothesis? Not really. Not successfully, and nobody was successful. That's what I mentioned. Nobody was successful in coming up with a hypothesis regarding the theory underlying the periodic table and everything else in chemistry. And so it happened by some other observations that the theory was developed. It came in an indirect way. They were looking at something else, and this is how the theory of chemistry came to be. What were they looking at? The other thing. I'm sorry?
I said, were they trying to turn it?
No. The alchemists were. Chemistry started off in alchemy, where they tried to turn lead into gold. So they tried lots of different things. But people devoted their entire life to that and weren't successful. There could have been people who devoted their entire life to studying the periodic table and trying to come up with some kind of hypothesis. Maybe they would have been successful, maybe not. But nobody came up with a hypothesis based on the periodic table that outlined the theory of chemistry. So, where is this theory? Well, what is the theory of chemistry called? And so these are the things, that make it very helpful for understanding things conceptually. For like multiple choice questions or conceptual type questions. You want to go back through and then have a visual picture. If you can come up with a visual picture of it in your mind, that's very helpful. And so the theory of chemistry, I already told you what the theory of chemistry is. So we were talking about the historical development of the theory of chemistry. What is the theory underlying chemistry? Theory is quantum mechanics. Where do theories come from? Do people just hypothesize a theory did somebody just come up with a hypothesis of quantum mechanics? They just said, okay, it came to me in a dream. No, it came through some observations. What was the observation that came from quantum mechanics?
Looking at light, right?
Right, they were looking at light, and so they were looking at light and light bulbs and that kind of stuff. I know Edison predates quantum mechanics. Quantum mechanics actually happened in the mid-1900s, way before Edison. Edison was looking at making light bulbs out of lots of different things. Not just Edison, but other people as well. Yeah. And so, Newton's been around. Newtonian physics has been around since the 1700s. Newton's laws of motion. Newton was one of the big physicists out there with Newton's laws of motion, theory of gravity. The classical, why they often say that quantum mechanics deals with very small things, very small things. This is why the classical physicists missed it, because classical physicists deal with very large things, relatively speaking. When you start to deal with very small things, then you have to worry about it. Like, for example, if you have a fish. If you have a fish in the ocean, the ocean's huge. Is there any restraint to how the fish moves? Can the fish move any speed it wants? Pretty much. Any direction it wants? Yeah, pretty much. Any speed within its limits. Well, what happens if, the body of water gets smaller and smaller and more restrictive? Then all of a sudden, does it matter? Does it matter the wavelength of the fish? How the fish moves? That kind of stuff? Does that matter? Yeah, it becomes more and more important. The wave properties, the locomotion of the fish, this is going to make a difference. Well, the same thing with an electron. If you have an electron in a huge ocean, a single electron, it can move any speed it wants. In fact, a free electron, unconfined, has a continuum of energies available to it. And so an electron can have any speed it wants, can move anywhere it wants, because it's unconstrained, right? And so a free electron, we say, has a continuum of energy. What does a continuum of energy mean, and what do we oppose that against? Versus a continuum versus what? Well, finite, I guess, or continuum. What's the opposite of continuum energies in the quantum mechanics sense? These are the things, that if you did this, you would ace every test. I mean, because if you get the basics, like the conceptual stuff, that's what I found to be 90% of the exams. Like at UCLA, if I could get an understanding of the lecture concepts like this, then for sure I felt I was guaranteed an A in the class. Because not necessarily the highest grade, but just an A. For some classes, that's all you want is the A there. If you want the top grade, then you got to do a little more than that. But I felt if I just got this level of understanding, that was enough. And what level of understanding? The level of understanding was just being able to repeat what the professor talked about in class in my own words. That was good. I didn't have to do any special advanced problems for that. And it pretty much held true for every class I took. But anyway, let's get back to this. So what we want to do is we want to go back and think about this. Well, probably the next day is not the best time to think about this. Probably right after class is the best time to think about this, because things are more fresh in your memory, and you tend to remember more. The worst time to think about this is the night before the test. The night before the test is that you're going to be suffering the most. But if you can get this log, and so this is what we want to do. We don't want to wait until the day before the test to get a grasp of what's going on. And so what was the unusual? Well, it was a light pattern. And let me tell you, it was an unusual light pattern. What was unusual about it? Well, okay. Quantum mechanics came from light patterns. Not just normal. Normal light patterns are what classical physics predicts. Classical physics predicts that the electron can move any speed it wants. And it can if the body is big enough. However, these were unusual. What made them unusual? What made them unusual was they violated classical physics, basically. This was a case where classical physics was wrong in its prediction. Classical physics was wrong. Did they abandon classical physics? It turns out they didn't abandon classical physics. Classical physics is just a special case of physics of like large bodies. And so if you take quantum physics and make the assumption that you're using or you're dealing with large bodies, then quantum physics simplifies into classical physics. And so classical physics is retained. This is just like us when we do Lewis acid bases. All acid bases are Lewis acid bases, but not all acid bases are Bronsted. What we do is we retain the Bronsted definition because it makes our life simpler. Newton, classical physics is a lot simpler. And so we retain that and then just work on large bodies. The error is minimal. So we don't expect much error. In fact, we can derive all the equations of classical physics from quantum physics by making an assumption that we're working with large bodies. But that's beside the point. This is not a physics class. This is just, we want to know where the theory of chemistry came from. So where did the theory of chemistry come from? Unusual light patterns. What made them unusual? Well, I probably shouldn't repeat yesterday's. We'll just move on here at this point, but maybe I need to stop sooner. I mean, not the day after, but sooner, the same day. Maybe we'll do that today. It'd be better. Today's material. But anyway, the main players in quantum mechanics was Bohr, and Bohr theory. Bohr theory, is that still around, Bohr theory?
No, they went away from it.
Yeah, Bohr theory turned out to be wrong, but not everything was wrong about Bohr theory. Some parts of Bohr theory were retained. But, the main people were de Broglie and Schrödinger. And also, earlier physics like Bohr, physicists, because they base the quantum equations based on the classical physics, but with some modifications. And so it is typically classical. One of the modifications for like Planck, Planck. You don't need to know these names. But it doesn't hurt because, of course, in general chem, you need to know the names. You need to know what they did. So it doesn't hurt to hear it twice. Once here, and then again in general, it makes it easier to remember. But anyway, we have come up with the Schrödinger equation. This is the equation of quantum physics, quantum mechanics. The Schrödinger equation is going to tell us what's going on with the electron. in other words, describes the electron as completely as you can. Describing the electron is very tricky, though. We want to know the energy, and we want to know where the electron is, its position. And so we see this, de Broglie was talking about the waves. This is like if you have a wave in a small box versus a wave in a big box. This is where we ended up. Then it makes a difference, how you move. If you're constrained, there's only certain movements you can do, whereas if you're in the big open ocean, there's lots of movements you can do. And so if you constrain it to a one-dimensional box, then it's naturally quantized. These energies are quantized. What does that mean, quantized? That's opposite of continuous. The opposite of continuous is quantized. Continuous is a ramp like this, a smooth ramp up. I didn't bring my book, but do you remember the woman that was standing on the ramp? They could stand any height versus stair steps. You remember that, or did you write that in your notes, maybe? The stair steps is quantized, the ramp is continuous because you could have it. And so the energies are going to be quantized. In a 1D box, do you recall in a 1D box, the lowest energy would be something like this for a string. The next higher energy would be like this, where we plug it harder and get a higher frequency. And then the next one would be an even higher frequency. But not all frequencies are allowed. There are forbidden frequencies and allowed frequencies, correct? And the wavelengths are going to be depending on this because it's got to start and stop at the same place. Start and stop here. So when we look at this, we could fit 1/2 wavelength, we could fit 2/2 wavelength, we could fit 3/2 wavelengths. But can we put 1.5 wavelengths in there? No. We can go all the way up until infinity. But what's going to happen is the difference. Let's say the difference between 1 trillion half wavelengths and the difference between 1 trillion and 1 trillion and 1. Is there going to be much of an energy difference between 1 trillion wavelengths and 1 trillion and 1? No. I mean, you barely even notice. Can you even see the difference? I doubt you could see the difference, here, because it's such a slight difference. That means the energy gap between here is so small, it's almost continuous. And so things kind of blend together up here, but down here there's pretty big gaps, pretty big jumps in energy. This is what we call a one-dimensional box. What about in a two-dimensional? Well, in a two-dimensional box, it looks a little different. So let's look at a standing wave in a 2D box here. So this, you might physics. These would be something like the resonant frequencies of the plate. It depends on how big this plate is. So we're going to do a two-dimensional plate here. This is a 2D plate. What they're going to do is they're going to sprinkle some metal filings on here. So metal filings will collect in troughs and stay away from. So they're going to be waves here. So we can see the waves using the metal filings here. It turns out, these waves are in a small plate, compared to the wavelength waves, so we can see. What frequencies are allowed, what frequencies are forbidden. This looks like an allowed frequency here. You see the wave pattern? It's a loud frequency. And then they keep cranking it up. And so they go to higher and higher frequencies, but nothing changes because this plate can't absorb those energies because of the size of the dimensions of the plate. And so forbidden, and eventually they hit a another allowed. And so this is the wave pattern on the plate from this allowed. And so they'll keep cranking up the energy. This is the next allowed energy here. And then crank it up higher, the next allowed energy. This is forbidden, allowed, forbidden. You know, all those were forbidden, allowed, allowed, this whole idea of forbidden and allowed energies comes naturally when we have a plate like this, you know, or small plate, big wavelength type deal. So that's what de Broglie said. Electrons have wave properties, and we have to account for those wave properties when we're looking at the
Today we're going to show you how to
electron confined in a bond. There's others. All right, so we want to know the energy, and we want to know something about the position. The position, you know, is going to be given by probability. Remember the bird's nest we talked about, the bird's nest. Unfortunately, you can't pinpoint the electron. You can only speak in terms of probability. Just like the bird, we can't pinpoint the bird, but we can speak in terms of probability based on its energy, right, of where it's going to be. Well, that's the same thing here. This is a result of Heisenberg. This is a result of de Broglie. De Broglie, we have the standing waves. Heisenberg, we have this bird's nest probability, cloud distribution. All right, so what we're going to do is we're just going to look at what quantum gives us for this. So for quantum mechanics, the Schrödinger equation this is not, the Schrödinger equation for the hydrogen atom is not hard to solve if you've had calculus. If you had some calculus, then you would solve it using differential equations. And from that, we can figure out all the allowed states of the electron. Each allowed state is called an orbital. An orbital is going to tell us about its energy and its position. Positional probability. And so for the hydrogen atom, it looks like this. And this is going to look a little different than your book does. Take a look. Actually, I don't like the one in your book. kind of the picture of the electron from the Bohr model. From the Bohr model, we have these. What were these called?
Orbitals.
Not orbitals, but orbits. These are orbits. And so from the Bohr model, we get orbits. From quantum mechanics, we get orbitals. Unfortunately, they shouldn't have picked those names. They should have called for quantum mechanics, they should have called it something else because there's a lot of confusion. People think orbits and orbitals are the same thing. They're totally different as far as visualization goes. And so here we have the first orbit. It's going to have the lowest energy here. And then these are the higher orbits. This is the infinite orbit here. So between here and here, we have an infinite number of lines, which means the energy difference between having n equals 1 trillion and n equals 1 trillion and 1 is negligible. We've got to compress in there. And so there's an infinite number of lines between here and here, which means that there's got a lot of lines right there. But anyway, there's big gaps here at the beginning. And so it turns out that based on this, on the Bohr model, the colors in the hydrogen atom spectrum come from this. So from 3 to 2, let's say an electron gets excited up to the 3rd floor. If an electron on the 3rd floor drops down to the 2nd floor, it emits red light. If an electron gets bumped all the way to the 4th floor and goes to the 3rd floor, it emits infrared light. But if it gets up to the 4th floor and drops all the way down to the 2nd floor, it emits green light. 5th floor to the 2nd floor emits blue. 6th floor to the 2nd floor it emits violet. So those are the 4 colors that we see, but there are a whole bunch of others that we don't see that are invisible. If something gets bumped up to the 2nd floor and drops to the 1st floor, that occurs in the ultraviolet. It's a little higher in energy, bigger drop. So it's UV. So there are a whole bunch of infrared, which are smaller drops, like 5 to 4 or 4 to 3, that's infrared. And then there's only 4 visible, but and there's a bunch of UV. And so that was one of the successes of the Bohr model. It predicted the ultraviolet spectrum should have a whole bunch of lines corresponding to these transitions. So there's only one allowed transition here, so there's only going to be one lone line positioned in several places. And then the infrared spectrum for this. And so we could see what those look like here. They gave them names. The names that they gave these, they called it, for example, based on the Discoverer. So the Bomber series. Look at the Bomber series. The Bomber series are in the UV. And so do you see that 3 to 2 transition? Oh no, 3 to 2. Bomber series, 3 to 2, that's in the visible. So we're okay. Bomber series. Then there's others, the Pashan series. This is the Bomber series. The red line there corresponds to an electron that was excited to the n equals 3, the 3rd floor, and dropping down to the 2nd floor. This is a blue-green line. 4th floor to 2nd floor, etc. Now, you can detect the invisible lines with a detector. And so what we could do is we could look at the other series. There are 6 named series, but we're not going to get them all. So the Bomber series was the ones that are in the visible. The Lyman series are in the UV. So this would be the Lyman series here. These are the lines in the UV. And so probably this one, let's see, this is the highest energy. The lowest energy one here is probably a 2 to 1 transition. Then the next one, 3 to 1, etc. So these are all dropping down. And so these lines are here, they can be detected, but they aren't visible to the eye. It's a Lyman series. You don't need to know the names for any of these series. It's Lyman Bomber, is the visible. Pashan series is infrared. So we have the Pashan series here. They don't give us the spectrum. You can see a composite here. It depends on who studied what part of the spectrum. But these are all the lines in the hydrogen spectrum. The visible and the invisible lines here. Shown here. As far as Bohr went, it depended on the orbits. And so we look at the orbits here, and for example, the Balmer series all end up on the second floor. So these are the visible: red, green, blue, blue, violet. Then we have the Lyman all end up on the first floor. Here, the bigger transition. The Pushon series here. This is kind of a visual picture of the orbits. What's happening with the orbits? Here's what we call an energy level diagram, which shows the drop. Energy level diagram. And so this is a nice picture, but it unfortunately came out wrong because it didn't predict anything. And so what we have to do is we have to modify this for quantum mechanics. So what does this picture look like? Quantum mechanics. So for Bohr, we have the n equals 1, and that corresponds to the orbit, right? So the visual picture is electrons orbiting. As far as n equals 1, we have like the floors of a building. And so n would just be on what floor. The higher the n value, the greater the energy, the higher the floor. In quantum mechanics, we look at this quite a bit different. In quantum mechanics, we have this. We have more numbers designating this. And so this is called n equals 1, L equals 0, and m equals 0. Well, that's kind of cumbersome. And so we come up with another way of saying this. Another way of saying this is called the 1s. It's not an orbit. We call it what? This is an orbit. This is the n equals 1 orbit. We call this the 1s orbital. And so what that looks like is this. If this is the nucleus, that's the bird's nest. And then surrounding the nucleus, the electron can be anywhere around there. And so what we do is we look at it over time. Electrons here, there, here, there, here, here, there, here, here. And eventually what we see is that the electron tends to spend most of its time close to the nucleus, and then a little bit of time farther away from the nucleus. Is there a wall that one of those PEP barriers? Is there a PEP barrier where the electron cannot be outside? No, there's no PEP barrier. Although the probability of finding the electron way out here is not that high. It's very low because the energy is not that high enough. But there is a chance it could be far out here. And so it turns out that the probability of finding an electron doesn't go to 0 until you hit an infinite distance away. I mean, there's the probability of finding it way out here, but still, that's not very representative. And so what we do is we make an imaginary boundary. Oh, shoot. The imaginary boundary is called a 90% boundary, or we could use a 95% boundary as well. But a 90% boundary or 95% boundary or 80% boundary, whatever boundary you want to use. Maybe a 95% boundary might be good. Maybe a 90. It's arbitrary. We'll just pick, because it's not a wall. It's an imaginary dividing line. This imaginary dividing line is just, okay, we're going to pick a boundary and call this this. And so what we say is that within this boundary, we have, let's say, 95% of the dots. Outside this boundary, we'll only have 5% of the dots. And so another way of representing the 1s orbital is as a sphere. It's not a hard shell sphere. It's just an imaginary boundary that says the electron should be found within this sphere with 95% probability. Does that make sense? And so this is a probability boundary, not a wall.
And so, like I said, it's a little bit cumbersome calling this a 1, 0, 0, n equals 1, L equals, we call it 1s. And so this is our 1s orbital in terms of electron cloud with the boundary here. And this is a 1s orbital in terms of just the boundary and ignoring the electron cloud.
What is L stand for? It's N,
This comes from the physics of this. And there's names for this, so eventually you get tired. This comes from the math of the Schrodinger equation, and L is just the variable they pick for the math of the Schrodinger equation, but it does have a physical meaning. The physical meaning of L is due to angular momentum. There's something, angular momentum is important. Conservation of angular momentum is important in physics, but we don't need to get that. In fact, we don't even care about the physics. We just want the end result. Now the end result here is going to be that this. Rather than having an n equals 1 orbit, we have a 1s orbital. Then there's a bigger jump to n equals 2. You know, in n equals 2, according to Bohr theory, the n equals 2 orbit's about 4 times the radius. But in quantum mechanics, it's a little different. In quantum, there's one energy here, but 4 different probability distributions that you can have for n equals 2. And so we could have n equals 2, L equals 0, M equals 0. And what that looks like is it just looks like a bigger version of this. A bigger version of this, well, it has more energy. More energy. If it has more energy, then yeah, there's a probability that the electron can be close, but there's going to be greater probability that the electron can be farther out. So again, what we're going to have is we're going to have a spherical distribution over this, and then we'll make our 95% boundary something like this. And so we'll call this the 2s orbital. The 2s orbital versus the 1s orbital, what's the difference? Well, they're both spherical. The difference is the size. You know, 2s orbital is a lot bigger than a 1s orbital. It turns out there are 3 more probability distributions that are possible for this energy. The 3 more probability distributions are this. We could have an n equals 2, L equals 1, and M equals -1. What does that look like? Well, what that looks like is if we had the nest here, it kind of looks like a figure 8 type deal, in which it's kind of weird, but it has more of a figure 8 type distribution like this, or dumbbell shaped distribution. And there's what we call a nodal plane here. There's a plane that bisects this that has 0 probability. In other words, it's what we call a node. A node is when the wave goes to 0. That's what we call it. We call these the 2p. So this would be a 2p orbital. For example, a 2p on the x-axis here. I think -1 is x. I can't remember. You know, it depends on how you define the coordinate system. But we could have something like a 2px, that is this. Because the next one that's allowed is an n equals 2, L equals 1, and M equals 0. So what that looks like is it looks exactly like this, except it's rotated. It's orthogonal to it. So let's put this on the z-axis. That is, we'll put 1 going up like this, plus z, and 1 going down like this on the minus z. If we're looking at a three-dimensional system. Or maybe I should have called it the y. You know, we have a Cartesian coordinate system like this. So this could be 2p y, let's say, maybe. I'm writing these dotted because there is definitely the -1 means x, y, or z, but you don't need to know. So it's not that. You don't have to make this association. Okay, and then there's a third orientation. It's n equals 2, l equals 1, and m equals -1. This is the next one that's allowed. And this one's going to come out of the plane of the board. And so this one, what does this one look like? This one looks like this. So we might call this the 2py. And then we might have something coming out of the board like this. So I'll try to draw one going out and one going in. We have 2 of the dumbbells or whatever. And so this could be the 2pz, the z-axis sticks out of the board. Does that make sense? Uh-huh.
So substitute that into a 1 and n -1 and that other one over there. What?
The difference between
No, that one and
And-
the one that you just drew.
the one I just drew,
Yeah.
this is the
Same
difference.
Numbers.
The numbers come from the math of the Schrodinger equation. Those visuals come from the actual visual, when you do the visuals. And so we have one in this orientation, and then just one perpendicular to that coming out. And so now you can kind of get a clue, you know, what does n really tell us? You know, if you put it in your own words, what does n tell you? N tells you the energy, We call n the principal quantum number, or the energy, principal energy level. And so the higher the n, the higher the energy. So n is the...
And what do you mean by energy? You like give it like temperature or something?
No. This is like potential energy.
Oh.
Could be like kinetic energy, you know, like this. To orbit way out here, this electron must be moving faster. To have a probability distribution that's farther out, the electron must have more energy. The bigger orbital has got to have more energy because what's pulling it in? The nest is pulling it in. For us, the physics is the nucleus is positive, the electron is negative. For the electron to escape the nucleus, it's got to have some energy. I'll use the same jargon as before. Oh shoot. So when we look at n is going to be the energy, the principal energy. This is called the principal quantum number, the energy. The higher the floor, the higher the energy. What do you think L is telling you? Just look at this and tell me what L is telling you. The shape. L is telling you the shape of the probability distribution. When L is equal to 0, it's spherical. So L is equal to 0 here, it's spherical. L is equal to 0 here, it's spherical. This S, what do you think the S stands for? A lot of people think the S stands for spherical.